15 research awards that I know about before that are geared toward undergraduate students. So that's and there's parts of the proposal. So some of this is technical stuff about where do you fill in the forms and where do you put your special qualifications for working for undergraduates and things like that. So a little bit of it's dry, hearing about the technical details of applying, but it's how you sell yourself. So it was good. So besides the ones through the Vermont Genetics Networks, these special opportunities through NIH Cricket Research Funding, which would lead to student work during the year, and student work during the summer. So kind of exciting. So it was a good meeting. So anyway, I hope you enjoyed the time. Did anybody go to the PME talk? A few people did, so that's good. I'll have another meeting during that time too. So, but anyway, today we're going to go on and talk about confidence intervals, right? So we've used confidence intervals a little bit on the class assignment through maximum likelihood. Now we want to understand a little bit more of the understanding underneath it and generate some new confidence intervals and see what's called the kind of classical formulas that would typically be taught. Right? So the homework 6 is due Friday. It has some problems on confidence intervals. It's a few more problems, but many of them are not too long. Right? Calculating an interval, writing a statement about what it represents, like that. So it's posted. Be available. So the idea of this one is we start out with we have some type of population. Right? And we're interested in studying that. And the population has various characteristics we'd like to know. And those are often encoded in parameters of a model. It could be theta generally. It could be a mean, right? An average. It could be a sample proportion. It could be a standard deviation or some other symbol representing something you want to know, right? And if you know the entire population and could calculate things, you might just report the average. Like if you actually do a census, you have what's the average savings account amount at Wells Fargo Bank, right? If you had access to all the records, you could just calculate it, and that'd be the number. But if you're doing an audit, maybe you audit, 1,000 or 10,000 records, and you still want to know what it is on average, and for various regions. So we end up taking a sample from that. Sometimes it's a random sample, so really representative of the population in theory, and other times it's more observational, more self-selected, but however you get it, you have a sample and you have data. In any real application, you probably measure several variables, but we'll just write down our measurements x1, x2 up to xn. In real situations, there might be correlation, clustering, and other things that affect that whole structure. And that kind of makes it interesting many times. But then we're going to have estimators. We're going to take our data we get from the sample and process it and get estimates of these things, and generally put little hats on those to represent the estimates of one form or another. They might be coming from maximum likelihood. They might be our unbiased estimators. They might be method moments. They might fulfill a number of those requirements. Right? And then the goal is to do statistical inference. So we want to generalize from the sample back up to the population, and we're making a statistical statement. Right? Because we know that our one estimate is not exactly that value. There's some uncertainty. So we want the best estimate, and then we want some expression of uncertainty. Right? So that's the big goal that we're going to have. And most of what we're doing in this chapter is kind of a frequency-based inference. Sometimes it's called frequentist. Inference, kind of the name that's given to this, the general approach. It's really dealing with repeated sampling. Oops. Thinking about repeated sampling what would things look like if we could take multiple samples over time, right? And it leads us to think about what is the sampling distribution of our estimator. We'll contrast this eventually to a Bayesian inference or just a pure randomization type inference to some degree. But mostly, this is very dominant and is used in most confidence interval statements, most hypotheses, that thing. But it's thinking about if you could do more random samples of the same size, same design, what would the estimators look like? How spread out would be, where their average is, and then using that information to come up to a way to produce an interval, to do inference going backwards. And so, in answering this, what is the sampling distribution? We've seen some ways where we can think about this. Right? We can do a bootstrap of our data, and we can get many different kind of replication copies of our data set as if we've done it repeated sampling, and get many different theta hats and look at the standard error, standard deviation of those, or look at the interval. Right? So that's one way to get an interval. And it's focused on doing something to try to get at that sampling distribution. Right? In chapter 7, it's more kind of a so-called classical approach. Because when this was all developed, people started thinking more about doing things rigorously. There were computers. Right? Computers were a room like this filled with people doing adding machines. Right? So you have, those were the computers, the people were the computers. And you wouldn't do something 10,000 times. Right? You would do it 100 or something like that. And even that was probably difficult in many things, right? And so maximum likelihood is one version of this. These are often derived from a bit of probability theory. So I'll drive through probability theory a little bit. So we will use a few probability relationships that are summarized in the book, and that we'll summarize here. Right? And once we do those, it won't be too much to figure out. Right? So the idea of how this in the 7.1 is we have our data, x1, x2, up to xn. And these we're going to assume are IID. Right? And IID is fairly standard statistical terminology, meaning that they're independent and identically distributed. So it's kind of like a random sample or a sample from one distribution. Independent and identically distributed. And we assume that they come with some distribution characteristics. So they have some mean mu and some standard deviation, sigma. Right? And if we want to estimate the mean, right, x bar is going to be our estimator of mu. It's unbiased. Right? The expectation of x bar, whatever the distribution actually is, whether it's normal or not, if each xi has that average and we take the sample average of those, then the expected value is that, so it's unbiased. We'll do this eventually with cases that aren't unbiased, and we'll work those out. 2, by the central limit theorem, right, if it is large enough, right, decent sample size, x bar is approximately normally distributed, and it will have a mean of mu, and the variance of, or the standard deviation of x bar, under this assumption that they're independent and they all have this standard deviation, is going to be sigma over square root of n. Right? So a little bit of probability theory goes into that. Right. So based on this probability statement, right, we can say where we think x bar is going to be. Right? Now we don't know the value of mu, which is kind of theoretically speaking, it should be close to mu. Right? It could be mu plus or minus a couple standard deviations. Right? And in particular, right, we can say something like 95% probability. There is 95% probability that x bar falls between the mean minus about 1.96 standard deviations up to the mean plus 1.96 standard deviations. And so why do we say that? Right? An understanding of why that's true, it comes from the normal distribution. Right? So we could look at that a little bit in R to see what's going on. But the probability that a standard normal is between negative 1.96 and 1.96 ends up being 95% approximately. So there is, so let's say we take just a random normal sample, and let's take 1 million values, right? And standard mean 0, standard deviation 1, right? So that's large, right? So the histogram of the standard normal is like that. And what is, to calculate the proportion that's less than negative 1.96, so how many of these z's are actually less than negative 1.96? Right? Is that out of 10 to the 6th, that's about 2.5%, a little bit more in this simulation. Right? How many are bigger than 1.96? Well, again, about 2.5%. But theoretically, the probability that a standard normal, which is calculated with this thing called p-norm, is less than 1.96 is about 2.5%. The chance that it's bigger, you can do 1 minus the probability. Right, so the chance that it's less than negative 1.96 is 1 minus the chance that it's bigger. That one's also about 2.5%. So under just a random normal, it should be about 2.5%. There's another function, q-norm, which gives the percentile, so the 0.025 percentile, right, of that, also called quantiles or percentiles, right, is negative 1.959964. So it's just about 1.96, right? And the upper one, 1 minus that, is about the 1.96, right? So another way of putting that is by 0.975, right, is equivalent to that, just that calculation, right? So there's about 95% of the random values that are in there, right? So if x bar is this, right, there's a result from probability theory that if you take x bar, a random variable minus its mean, divided by its standard deviation, it should have mean 0 and variance 1. Right? And linear combinations of normal are still normal, so that's the standard normal. So that's where the negative 1.96 and 1.96 comes from. Right? So what we do then is consider this interval that has 95% probability. Right? Well, we have two statements. Right? Here's one inequality. You could change this inequality to isolate mu. Right? You could add this to both sides. Right? So you'd have mu is less than 1.96 plus that. And you can consider the other half of this. Right? Here's x bar less than or equal to that. Well, you could isolate mu again by subtracting that to the other side. If you do both of those things and you get mu is greater than something and mu is less than something, you can stick them back together. And that's not going to change the probabilities. That's just going to just rearrange things a little bit. Right? So what we get when we rearrange inside the probability statement, we can write that the probability that x bar minus our 1.96 sigma over square root of n is less than or equal to mu is less than or equal to x bar plus the 1.96, right, sigma over square root of n. Should still be about 95%. And so if we knew sigma, right, if we knew the standard deviation, if there was some kind of physical property of the measuring instrument or something like that, if sigma is known, we can report what's called the 95% confidence interval for mu as our x bar minus 1.96, and then this sigma over square root of n up to x bar plus the 1.96 sigma over the square root of n. And treat that as an interval where we think mu is. Right?
So I think you said once that like the parentheses versus the brackets, they don't matter.
Yeah, it won't. It won't matter too much. I mean, it might be exactly at that point, but if it's continuous, then it's not going to be exactly there. Right? And often in a lot of practical studies, there's a lot of things going on: sample selection, non-response, imprecise measurement. There's also just the random sampling. So we hope that that captures where it is. Right? And if ever you were really concerned about something that ended up right at that edge, then you're going to have to think about that, because maybe your real mu is a little bit higher than you thought, or maybe it would be a little bit lower than if you thought it was right here. So if it's right at the border, maybe it'll be included or not. But if it's just a little bit on either side of it, it's still kind of in the same place. So, but we're because of it, if we random sample from a standard normal, we get 95% plus or minus 1.96. And so, or 95% of the time we get x bars in a certain interval. Also, we think that about 95% of these intervals actually contain mu, right? But we change philosophy a little bit, right? In that the random sampling is on the x's. The x's are random, so x bar is random. Whereas we think of this mu as the real characteristic of the population. It's the real value that's out there, right? In physical science or nature, it's some real constant. If you really had a population and could look at the entire population and get that value, that would be it. And other times, that interpretation as a true value or fixed value is a little less, but we think about this as an interval. And one way to think about that is we can get some data and calculate a value of x bar, and if we know sigma, then we're going to stick a little interval on it. Right? If we'd got a different value of x bar, right, we'd stick an interval on that. Okay, that's where we think mu is. And so, or maybe one's over here, and here's the other intervals. Every once in a while, we're going to get an oddball, strange samples, with few extreme observations, and it's out like this. Now, somewhere is the truth. Right? Somewhere is mu. Right? And so, as it's drawn here, it'd be probably pretty reasonable to put mu somewhere kind of like that, right? And these three intervals cover. Right? These three random intervals. The intervals are actually random because the center is random. Right? These cover, this one misses. Right? And we call it 95% confidence because we say we're 95% confident that the intervals actually cover. Right?
So that would be 75%.
That would be 75%, yeah, but I could do kind of ... and maybe there's others, right? So, but right, if we had 100 intervals, we would expect about 95 to cover and 5 would miss. Some would be too high, some would be too low. 2.5 up here, 2.5 down here, right? 95% confident that the interval covers the true value of the parameter value of mu. And there's a kind of little formulaic statement, because it doesn't mean there's actually 95% confidence that the interval covers. Right? Each interval covers or doesn't. It's kind of 0, 1, good or bad. But over the long term, over kind of the repeated sampling, the frequentist property is 95% cover. Right? For a while, I graded for the AP statistics exam the free response, and students were supposed to write an interpretation of a confidence interval. And if they said there's a 95% probability that the interval covers, and it's not quite right, or 95% of the data covers, no, this doesn't cover 95% of the data, the interval for the average, and 95% of the time these intervals should cover. So there's a little bit of formulaic thing in there. That's kind of what you get. And generally it works, should work quite well. So I have a little numerical example. If you take boys age 2 years old, so 24 months. Right. If you look at the National Center for Health Statistics growth charts, they report that the average was about 28 pounds. Let's say that's mu. These are hypothetical data. I don't actually have birth weight data, but it's about 28 pounds looking at that chart, right? And the standard deviation I judged from that chart to be about 2.9 pounds, approximately. If you kind of look at the 90th and 95th, the 5th and 95th percentile on that chart, you get kind of a distance, so that's a certain number of standard deviations. And so I think it's about 2.9 pounds. Right? So if this is about 3 pounds, plus or minus 3, plus or minus 6, so the boys would be, most of the 95% of the boys would probably be 22 pounds up to about 34 pounds. It's kind of a range. And of course it varies by height and things like that. But let's say we sample n equals 40. Boys, and you calculate an average of 27.2 pounds. What's a 95% confidence interval based on our sample? 95% confidence interval for average weight. In the population. And so looking for that average of mu. So our formula is going to say, take the average plus or minus a certain number of standard errors. So we want to calculate x bar plus or minus 1.96. Right? 95 tells us 1.96. And then sigma over the square root of n. So if it's a matter of just putting in the numbers. Right? So 27, look that up. 27.2 plus or minus 1.96. And this was 2.9 over the square root of 40. This is 27.2 plus 1.96. And this number, this standard error, is 0.4585. That's 9, rounded up, right? And so this is 27.2 plus or minus 0. About 90. Round up to be 4585. Yeah, I'm not quite totally sure about that, but right. Oh, right, 1.96. It's not doubled, right? So that works out, right? And so this ends up being 28.1 and 26.3 pounds. And you could take it to another decimal place, perhaps, but going much more beyond that probably implies a little bit more precision than when we actually have. 3 decimals maybe, but and so you're 95% confident that the actual average is in there, and this would be a successful interval because it would cover. Right? Maybe we would like it narrower, but with 40 observations and a standard deviation of 2.9, we just can't make it defend it any more precisely. But any questions on? So how does the interval change? So if we have n equals 40, and we had x bar 27.2, we got 26.3 up to 28.1 pounds. What if instead we'd have a different sample and we'd got 27.6? Is it clear how the interval would change? have been higher, right?
So we just do
Yeah, it's still x bar plus this, so it's still plus or minus the same thing.
0.9.
Everything's scooted up a little bit, right? So it's 26.7, 28.9 pounds. Again, that's good. 28's in there. Now, what if we'd gotten 40 samples? What if instead we'd had 28.95 as our average? That one, it shifts it over, same width, 0.5, right up to 29.85. So if we've taken these 40 boys from a particular hospital in a particular area where they're either taller or a bit more well-fed or something, maybe there's more, less poverty, maybe there's more prenatal care, something like that. And they're heavier, and that was our sample of 40. This average would be a little bit high, and we'd miss the 28 average. Maybe it's the nature of the sampling, or it's just random luck, right? Every once in a while, you do get one that's out there. You can think about how these other, factors affect this, right? Certainly, if the standard deviation had been bigger, if we had a more variable population, you're going to get a bigger sigma. If you'd taken this to a little subset of the population where everybody was more similar and it'd be, there's less variability, there's not the extreme lows or extreme highs or something like that, or maybe just the extreme lows for birth weight, then or weight at this point in time, then that would be smaller and the interval would be narrower, or sample size. Sample size is the big driver, right? So you can also see what would happen, right? Say you had 400, if this x bar equals 27.6. With 27.6 at 40, its mu is clearly in there. What happens if we do this one?
Smaller.
It's going to be smaller. Yeah, 27.6 plus or minus our 1.96, and 2.9 is still the same. Now square root of 400, 27.6 plus or minus. Now the margin of error is 2842. And our interval is 27.32 up to just 27.88 pounds. So again, that one would miss. We would expect 95% to be good and capture the thing. So I have more misses than you would typically have, right? But this one's a lot narrower, 27.6 covered. So we want coverage, we want 95% coverage. We also want it narrow. Maybe this is a population that is a little bit lighter for some reason than the average. Maybe it's an unusual sample. You really can't tell unless you know more about where the data is coming from. Right? But anyway, this would be the kind of how it responds to that, right? When you get ready to do a study, what error do you want? What margin of error do you want to have? Study planning. Our intervals have x bar plus or minus m, where m is, margin of error. And this margin of error is our normal value times sigma over the square root of n. So we can choose a margin of error. We'd like plus or minus half a pound, plus or minus quarter pound, something like that. And then figure out what the sample size should be. Right? So if we square both sides, and then solve for n is 1.96 squared, sigma squared, multiplied by n on both sides, and that one cancels. And then divide by margin of error on both sides. We get a formula for sample size, right? So what we know about the sampling distribution from theory tells us something about how we should plan the study for a certain accuracy. So if we wanted, if sigma, if sigma is still the 2.9 pounds, and we want a margin of error to be, 0.4 pounds, right? 0.4 pounds, right? we'd have the 1.96 squared, 0.4 squared. Oops, that's the wrong number. 2.9 is the sigma. 2.9, and then 0.4 goes into here. So this thing's going to give us 201.9. Right?
We would have to round it to a whole number, right?
Yeah, I'd probably round them up. Right. The conservative thing is round up.
And that if it's people in the sample too.
Yeah, right. So people or units, right? So if you get 202, even if this had been 201.1, I might still round it up, right? Just because you want the intervals to be no wider than that. The bigger sample size, the narrower it gets. If you go to 201, it's a little bit less, a little bit wider. You can do some planning. 95% is typical, but it's not required. Early in the debate about what was significant or what levels you should look at, there's actually an interview. They asked Sir Roland Fisher about what he thought significance was, and he said, oh, probably 5%. And they wrote 5% as a good example in their 1930s research workers, statistical methods for research workers. So 5% have been pretty standard. 5% is somewhat unusual. 1 out of 20, it's not something every day, but it's not overwhelmingly significant, right? It's not overwhelmingly rare. Right? You can have 99% coverage. You can have 90% coverage, but there's a price to pay, right? So 95% confidence intervals, we use the Z cutoff value. The book calls it Q for the quantile associated with the 95%. Other places will be, put 0.025 for the 95%, the upper 97.5 tail. So other places will have different notation for that. I don't know if I've ever seen it just called Q. More often I've seen it called Z, but whatever. It's just a multiplier there. Right? Or 90%. And these things will come here, the x bar plus or minus the Z value, sigma over square root of n. Right? So we want 99%, we need to have more coverage. We need to have more of the area, more of the random samples have to be included in that. Right? And so this Z value, right, we'll do it in parts, get it here. Right, the Q norm, normal quantile that has, now if it's 99%, there's 1% left over, right? And so that means there's 0.5% on each side. So 0.005 is that number, right? It's about 2.576, right? 2.576. And many textbooks will give that as the number. You could round it to 2.58, but it's like this. And the 90 percentile is about 1.645. Right? So if you want to have more confidence, which is a good thing, you'd like 100% confidence, but you need to limit it. You can't make it infinitely long. You make it wider. How much wider? Well, it depends on the sampling distribution and the probability distribution of Z, right? So in these pictures before, where we missed, right, where's my little, this picture that missed, if we wanted to do something like 99% confidence intervals for mu, it's always confidence intervals for a parameter, we would have a bigger multiplier, so they'd get just a little bit wider. Right? So all of our intervals would pop out here just a little bit more. Right? And then some of them that missed before, because we made it wider, used a bigger Z value, do cover. So more cover, but at the price of making the intervals wider. There's no right or wrong. It's just a trade-off. Right? You always report the level of confidence, so people know what Z value you used, right, in that. That's the basic idea. So what if sigma is not known? Right? Sometimes you get a little pilot study or previous research. You know about the field. So maybe you use that for sample size planning. Right? So you can still kind of do that. But we don't want to make intervals just based on that. So what if sigma is unknown, and it usually is, right? We're going to estimate that by the sample standard deviation. By S, where S squared is 1 over n minus 1, the sum of the xi minus x bar squares. And the S is our sample standard deviation. Right. So we're going to make our new interval as x bar minus some multiplier. We'll put a t in here for now, s over the square root of n. And then an x bar plus a multiplier called t, s over the square root of n. So we replace our sigma by our sample value, right? And think about what it is. So our standard error is replaced by the sample value, simply plug that in. Right? So now probability theory comes back in to tell us a little bit more. Right? And we'll do that in just a second. Right? So there's the probability theory that if the xi's are normal and independent, probability theory says we have the xi's, if they're IID normal, centered at some mean and some standard deviation, then if you take x bar minus its mean and divide by s over the square root of n, right, that this thing has a t distribution of n minus 1 degrees of freedom. Right? So this thing, this statistic, is distributed as a t distribution with n minus 1, what's called degrees of freedom. Kind of an index based on sample size. There's infinite number of different t distributions. They depend on a certain parameter, actually. And it's indexed by sample size, minus 1. Right? Why minus 1? Well, you're estimating the mean, so you're kind of using up one bit of information, and there's n minus 1 left over. There's a linear algebra take on this, where you have endpoints that kind of are in dimensional space, and you're projecting them onto the mean, and so there's n minus 1 free dimensions. So there's kind of a mathematical way that this comes about. But what does this t distribution look like? Well, it looks like a normal. If n is over 40, you visually have a hard time telling them apart. Right? But the t is wider, so let's say that this one is if this is the standard normal, note by z, then this, they're both centered here at 0. A t with a smaller number of degrees of freedom is smaller in the middle and bigger on the tails. It doesn't actually go up, it goes down 2. It's t with something minus 1 degrees of freedom. So there's more probability out in the tails. There's more area away from the center. So the percentiles to get 95% have to be spread out farther, right? So let's look at that in R a little bit. So I'm going to do a t sample. So let's do RT is random t. Let's do a million points again. And let's use degrees of freedom not too big. Let's say 9 degrees of freedom. Small sample size 10, right? The histogram of t doesn't look too big, but it looks like we've got some points that look kind of crazy big or small for it to draw it like that. Right? What's the range of our million z values? At a million values, you eventually get some that are pretty far away. Right? But the range of our t values is much bigger. Right? With that. What's the sum of the z ones that was less than negative 1.96 was about that number. How many of the t values are less than that? Quite a few more, right? And bigger than 1.96 similarly, close to 2,500. The T's, again, it's 41,000, right? So it's more 4% instead of 2.5%, so it's more spread out. The quantiles for the T, the 0.025, 0.025, and you put degrees of freedom, so if it's 9, it's negative 2.262. Right? If it's 39, like our sample of 40 boys, right, that would be negative 2.02. So it's just a little bit wider. Right? If you do 1 minus that, it's 2.02, so a little bit more on each. So you go out a little bit further to get the 95%. So the impact of that, right, on our intervals is, what did I say? There it was, right? We're going to put that T value in here. So it's a little bit bigger multiplier. So if S is the same as kind of the theoretical idea one, you're just going to make your intervals a little bit wider. Why are we making it a little bit wider? Why does this make any sense to use wider intervals? Well, you can think about it. Instead of knowing sigma, we have to estimate it. We have to get one more piece of information from our data for this to work. And sometimes S is small, and sometimes it's big. When S is small, smaller than sigma, our intervals are narrower. So there's a chance that it wouldn't cover. Right? So to compensate for that, T makes a bigger T value makes it a little wider. Right? So it compensates. And it compensates in a specific way to make it work out. Right? So in this example, still on green, if we had our n equals 40 and our average was 27.2, let's say our standard deviation was 2.8, our sample standard deviation now, right? Then we'd say we'd use degrees of freedom of 39, right? The 2.5% tail cutoff with 39 degrees of freedom. And different books will write this differently. Usually there's a degrees of freedom and some type of tail. It was about 2.02 there. And for precision, you could keep a third decimal place, or if you do it on the computer, you keep all the decimal places, right? So we get 27.2 plus or minus 2.02. And now S over the square root of n. And so 27.2, this turns out to be 0.89 for keeping it that one, or with a little bit of rounding, 26.3 to 28.1. And that works. It includes 28. Normally you don't know if your intervals cover or not, because you don't know the truth, right? But you just behave confidently as if they do, unless you have some evidence that suggests that things have gone wrong, right? Now, if you change sample size, something else happens, right? There's kind of another interesting, right? Sample size being different, say we had 80, right? You can have square root of 80 here, so it's going to be more precise. Is there any other reason it's more precise?
Because now the degrees of freedom are larger.
Yeah, now you have more degrees of freedom, so this thing depended on degrees of freedom. So you get an extra, bigger sample size helps you in two ways, right? Sample size there, but also the T value changes. Right? So every interval depends on sample size. So if we have n equals 80, then we use degrees of freedom of 79 in this case. So the T value we want to do, let's look that up. Here. Right, so QT 0.975 and then 80 minus 1. 1.99. So it's a little bit smaller, right? .99. So now we'll do 27.2 plus or minus 1.99. 2.8, right? That was our value of S. And then the square root of 80. And I calculated that one. Oh, I didn't calculate that one. But it's 27.2 plus or minus. I have a margin of error thing, but not that. 27.2 plus. You kind of do this plus or minus 1 works there. So 1.99 times 2.8 over the square root of 80. And you get that interval there,
Which doesn't come.
which does not quite cover. Right? So if it's 80 at the same mean, it hasn't got closer to 2.8, then it doesn't quite cover. You can put the quantiles in here and not deal with calculating, typing the numbers. You could also say n is 80, and then put this thing here. So this is n minus 1, and this is the square root of n. So I can change n now, and then just throw it into that formula. And so in R, you can kind of automate a few of these things. So. But that's right. That's the adjustment. Does this work? Does it seem to work and cover? So the question, does this procedure work? Right. What is this procedure for making a generalization about mu? What do I mean by work?
Is it justified?
Is it justified? But what, how would you know if it's justified? Certainly our data are not always going to be normal, but we don't really need total normality. We have central limit theorem, so we get a reasonable sample size. But how do you know you have a reasonable sample size? You might bootstrap it to see if the sampling distribution looks normal. Right? But to keep this, we want 95% coverage. Right? And so you could put at least there. If we had 96% coverage, it still would be 95, at least 95. Right? If it covers more often, that'd be great, but not wider than necessary. I can't tell you that this is the absolute best thing to do all the time. If you have small sample sizes and it was kind of skewed, maybe you could come up with a different scheme that works a little bit better. Maybe the bootstrap and small sample sizes where things are allowed to be asymmetric, maybe that works a little bit better in some cases. But this procedure, if you simulate it under different distributions and different sample sizes, you could see, do I seem to cover pretty well, right? So if you generated 10,000 data sets from a chi-square, which is skewed, or from a binomial, which is discrete, for a certain sample size, and did in intervals, and at least 95% of them covered, at least it would meet that first criteria, and generally these are pretty good, because tying something to the actual sampling distribution is usually pretty good. One other thing that other people have researched this, right? Including right from the start. Oh, so that's there. So this t distribution, right? Students t distribution, right? Is in Wikipedia, which is, it's fine to look at that for some sources. And so there's a whole article about it. Student was, this was student. This is William Gossett. So back in ancient history, people worked with a major professor or mentor or something, and things got published under their name, and they took credit for it. And so he published as student, kind of anonymously. He worked for the Guinness Brewing Company and dealt with small samples. Was aware of work that Fisher and other people had done about this confidence interval business. And so he published a paper in Biometrica that proposed this adjustment, right? And so that paper is referenced in here somewhere. So let's see. Student, William Gossett. So JSTOR, right, is there. Biometric, or the probable error of a mean, right? Right, so this is the frequentist idea. Any experiment may be regarded as forming an individual of a population of experiments which might be performed under the same conditions. A series of experiments is a sample drawn from this population. So you can get this kind of repeated practice over time, and there's a lot of text. If you get the PDF for it and see the whole article. This journal Biometrica still exists and is still one of the premier journals in statistics and probability. And so it describes a number of these circumstances, and then so it goes through with notation that's a little bit different. So sample, standard deviation, that's the formula we would have. But so it's typeset a little bit differently. But these things look like moments, don't they? And things like that. And it goes through and gets a probability formula that's very close to our current t-distribution that you'd see in books and so on. Right? And then they go through practical tests of the foregoing equations. So they do simulations back in 1908 to see if this works, which is kind of amazing that you would, because there's no computing, right? So you have to do everything by hand. So they have a table containing height and left middle finger measurements of 3,000 criminals, and then they randomly ordered them to study its performance, kind of a bootstrap almost, or simulation from this set of data. And they go through that and evaluate it, and they have all these tables of frequencies of which things happen. And look, they have a normal distribution, and this normal is t through simulation. A whole lot of work to do that, right? And then tables for cutoff values, I think that was there, right? Percentiles based on sample size, and again, very small sample sizes. You don't want to waste a lot of year doing things, I guess, right? And then illustrations of the method. And so the conclusion, does this work? A curve has been found representing the frequency distribution of standard deviations of samples. That's actually a chi-square distribution. And then a curve representing the values of the means relative to the standard deviation. That's the t-distribution. And the curve represents the facts fairly well of that distribution, even when the distribution of the population is not strictly normal. So some deviations from normality can be simulated, or if the actual data are not quite normal. And then tables, where it works pretty well. And Carl Pearson's another big name, so like chi-square, Pearson's chi-square statistic, Pearson correlation. So anyway, he did a simulation back in 1908, and it seemed to work quite well. And at that point, with promotion by Fisher and Pearson and other people, kind of became the way to do confidence intervals for me. Right? So anyway, that's what's meant by performance, right? If you could do it many, many, many times and had some sense of the truth, either because you assumed a distribution or because you had a big population and you were subsampling from that, right? 3,000 criminals, take samples of size 30. How many intervals, what percent of the intervals from samples of size 30 cover the 3,000 average, right? And if it's near 95%, then that's kind of what you hope for, right? And it does just marginally better than a normal interval, right? Instead of using the normal 1.96, smaller sample sizes get more advantage, right? Sample size of 200, there's hardly any difference, right? Sample size of 10 or 20, there could be a bigger advantage. That's it. When we'll come back and we'll look at how this gets used for differences of means, proportions, different proportions, and different varieties of having a factor. Oh, okay. So you'll have, for the stats, you'll have a math class, and PPP1,
Yeah, no, this is completely done for this semester. And if they don't like how much of overlapping math, I can have econometrics fill as the fifth one.
That's right. We talked about it. Good.
So, all right, thank you.
Thanks, Vic.
Thank you.
Yeah, this has been 2 years delayed now.
Well,
If it been
It
just
counts
kept
at the
putting it
end,
off.
right?
Like,
Yeah.
oh, yeah, exactly. Counts at the end.
Well,
Thank
you
you.
know, and if you're applying for jobs and things,
Oh, I've just been putting it on for
Oh.
jobs and stuff.
well, good.
I'm like, yeah, I'm gonna do it. I'll get right on. Thank you.
Yep.